Yeah, because we just covered unit 6 and 5 just recently, right? So it is still fresh in your mind. Okay, so that is the intent here. Let me move fast. I think I put some exercises in unit 3. I don't know if I did any exercises in unit 2 per se, but there are some illustrations of slides. I would just probably highlight 1 or 2 slides of the illustration, and then I say, okay, rest of the slides you convince yourself. Okay, you're not getting, what are you not getting? You're not getting my voice. Okay, let me check. Okay, can you hear me? Until now, Jntuk Kakinad and I were interacting, so I assume the audio was working. Jntuk Kakinada, can you hear me? Can you just put it in the chat? SVCW is not able to. Okay, Jntuk Kakinada is able to hear me. SVCW is not able to hear me. Chakravarti garu, you are the problem solver with respect to audio. Kada. Please let them know what they need to do. Okay. Okay, now it's getting the voice. Excellent. Okay, great. Okay, I'm going to move it. Okay. Okay, here is an example. Students, you just have to follow. What are we doing here? And let me go back just one step here, right? We are going to talk about binary search, a quick merge sort and quick sort. That's it, divide and conquer. Nothing much we are going to talk, right? We know what divide and conquer means, right? We'll see that. You have a big phone book, 1 million records, okay? Replace Manhattan with maybe Kakinada or India, whatever, right? So the question is, we need to locate a name quickly if you're looking for somebody in that directory, right? Okay, and the entire thing is ordered, right? Remember, the telephone book is always ordered, right? So how do we do that? So the basic algorithm is basically repeated halving. Okay, so to look at somebody's number, in this case Patrick's number, right? You're most of the time you're opening the middle of the directory. Okay, so we compare it against Patrick's name, right? If it comes before means you follow the left side. The entire right is ignored. If it comes after the first entry, in the middle of the entry, then you rip off the left side and do the other side. So what you are essentially doing is you are basically dividing it. Every time you are searching for the name, you are dividing it by half, right? That is as simple as that. So if you started off with 3,000 pages and you're looking for something, you're left with 1,500 pages. Next time around, 750 pages. Okay, so you can see how it is that is the binary search as we talk about. Okay, so you can see how drastically it's no longer a linear search, right? Remember, when we talk about linear search, we said if there are n entries, the order of n out. Whereas in binary search, it's basically log of n, because you're ripping half of it. Okay, that's the essence of it. So repeatedly halving the size of the search space is the main idea behind the method of binary search. Okay, if some question comes up in your exam, I assume something like this would come up. Okay, obviously saving is significant, right? You can see, 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 you can you can see the difference between n and log 2n. We covered that in a lot of detail. Okay. So there are some bunch of slides here where it shows you a nice illustration, right? So you have it has to be sorted. Number one, it has to be sorted. We are looking for what, 70. So when you divide it using the floor ceiling concepts, somewhere you are coming, right? See the different arrows here. Okay. So you follow this thing here, and then let me see how the illustration moves there, right? So V of middle is less than or equal to X. Okay. So then you are going to throw away the left half. Okay. That means now you focus only on the right half. You can see the illustration there, right? So you can seeing X is less than or equal to V of middle. Okay. Now you throw away the right half. Okay. So see how things are getting narrower and narrower and narrower there. Okay. And then you keep track of the pointers. If both right and left point to the same thing, that means you have reached the destination. Here is an algorithm for binary search. Remember, when we talked about these things, I showed you a lot of pseudocode. I said, hey, typically here, at least when we teach, we always have the students implement these algorithms, so that way they get programming practice, right? How is mid being calculated here? You can see how the mid value is. It is the floor, right? 4 is the largest integer. How do we formally define floor, Andy? Chakravarti garu? It is the largest integer less than the value that we are looking for. Okay? 1 less than the value that we are looking for. That is the floor. Okay. Floor, that's where you put the pointer, and then you are checking what you are looking for is less than or greater than. That's why you see 2 if then else's. So you move both the left pointer and the right pointer, and you are in that loop while r minus l is greater than 1. Once it is 1, you stop. Okay. Now, how can we do binary search? First of all, we said the condition is it has to be sorted. Okay. Now then that means sorting means it takes time to sort, right? Okay. So we need to sort a vector or an array, as you call it, so that we can use binary search. Lot of different algorithms for sorting, right? In the very first class, we talked about what I asked you to implement programs for selection sort, bubble sort, right? So here we are going to look at 2 sorts here today. Okay. The reason is this is a classic. Both these examples are they illustrate divide and conquer approach. So we look at merge sort here. Then each one again is further broken down into 2, right? Same logic.
was listening to the Moocs lecture here. Very clear. It's a lady voice. It was a lady. One. Oh, yeah. That was reflecting on this. Oh.
Okay, can you hear me now? I don't know how the system muted me. Can you hear me now? Perfect. Great. So as I was explaining, I was showing you the illustration of merge sort, right? Where you are taking, initially to sort, you are taking the top-down approach where you had a big array, you broke it down into two, then you went down further, ultimately you were left with leaf nodes. Then bottoms up, you started merging each of them. Okay? That's how we went. And then I showed you the algorithm, and then this illustration shows how the algorithm is really working. Okay? The student just have to go to the algorithm step 2 entries to convince them. Okay? Okay. So I'm not doing anything special there. It's a pretty standard algorithm. So when you're doing that sorting and then you finally have to merge, there are a bunch of sub algorithms there. Take a look at that. Because remember, you have a left subtree and a right subtree, so it's showing you a function for both left subtree and the right subtree. But the top function is only one merge sort function. Okay. At the highest level, that's what it is. So you have a main function merge sort, and then since you learned some programming, you know this, right? So when you write these recursive algorithms, so you have the main function merge sort, and then after you divide up, you have a y left and a y right, and left thing would get 1 to m entries, and the right thing would get m plus 1 to n entries. Okay, and then once those two functions out, you have to merge those two. So at the highest level, this is your main. If I want to call it main, what you're seeing is the main thing. Okay. That is merge sort. Great. So suppose n log n is the time complexity for that, right? As somebody was pointing out the other day. Okay. Now how is that different from quick sort? Both are actually equally capable. Both give pretty much the same orders of time complexity. Okay. Now depending on the data set, how the data is coming and so on, there's a lot of research that tells us, hey, in these types of situations use merge sort, in these types of situations use quick sort. I did not really put down those situations in a review slide, but you are welcome to Google it up and see which one is quick sort works slightly differently. The concept, what is the concept of a quick sort? You take a pivot, right? There's a concept called pivot, right? Once you take a pivot, you see the numbers which are less than the pivot, you put them in one array or one side, and anything greater than that you put on the other side. So again, you have the concept of left and right, different subgroups. So here you are taking, like if you have an array of numbers here, 7, 4, 9, 6, 2. These are the numbers, right? And then what we are seeing is our pivot is this underlined one 6. So what is the first thing that you do? You take anything and then you go from left to right. Notice one thing here, the numbers are not sorted. In the merge sort, when we did that, the array has to be sorted. That's the reason why you get the n there, right? Because when you have array n, sort that array n in order of n. After you sort it, you're bringing it on trees, right? I'm just applying rule of thumb. The moment you talk about tree and going to the depth of the tree, the moment we talk about depth of the tree, we know it is log n, right? Remember we talked about binary? It's a log n. So you, at every level of the tree, you are doing n actions, and then you're going up to log n depth. That is the reason how you get n log n. Now when you come to quick sort, you take this pivot here. Anything greater than the pivot, so if you start, you say, hey, 7 greater than 6. Yes, so you put it on the right side. Next is 4. It is less than 6. Put it in the left side array. Next is 9. So 9 goes to the right side. 6 of course stays in the center. Right? We'll see that in the next slide. And then 2. 2 is less than 6. You put it here. So what did you get here? Basically you got a left subtree, right subtree, and then the middle one. Okay. Now, once you have an element here, you have to remember at every level you have selected pivot. So in this case, you selected the pivot 4. Okay. But once you have pivot 4, 2 it is greater than 2. So you put that in this right. I don't think you don't see the number here. Actually, I put the number 4 there. So then you get the 2 there. Okay, that is the essence of it.
Of my research. And then you have come here. So you could impart you proposed a model to the principal secretary in Jntuk requirements. And for some PhDs and joint MScs, it should not be the conventional course, but it should be a learning center course covering these aspects. So that is the outcome of this. So because of this, the state government got inspired and they have come over planning to visit there, so that if the policy making bodies are interested in doing this job, that will be more fruitful and realistic. So this is the outcome we can mobilize the society as well. So that is how I want to represent. Do you agree with me on that? That you can add anything or you can amend anything. This is the broad outline on which I want to work. And then what we will do is another step is, so this is the outcome to this. Now we have to submit a letter to UGC asking for extension. Then we will say that now we involve the state government. So probably the state government may require a couple of visits, maybe even senior visits, initially in these visits. After that, maybe for some technical discussion, some of the principal investigator or somebody may need to visit sometime in April, May again. Maybe some election times. So for that sake, anyway some amount is left, one person is not there. So we will push it to the next thing. And then maybe a visit can be, from these people can be extended. So we need permission to extend this till June. You release the quota remaining. Until you release the quota, you may be permitted. From the next budget, also you can permit us. Both the hospitals. This one slot we will use in April, May. If a visit of PA is needed, and if visit of more than one person is needed, we will draw from the extra quota next year and will permit us to spend this before, and we will adjust in that. That's how we So that is one letter we have to draft. So these are the things, sir. So you can draft from your way, your own way, and I can draft, and we can just communicate to each other and refine them and something like that. Maybe we will have fixed the target as 4 or 5 days for this. I think it's a okay. But for UGC, what are the
muted now. Can you hear me now? Let me test my audio again. Okay, glad. Yeah, blame it on WebEx. WebEx is not perfect. What can I do? Okay, so what did I say with quick sort? I hope you heard or at least saw the slide there, right? So we choose a pivot element and then we break it down into two subgroups, three actually. One is all the equal members of whatever the pivot element is, they are put in one set. Anything less than are put into the left set, and anything greater than is put into the right set. And then you continue to recur on the left set and the right set. Okay, less than or greater than. And once you reach up to the leaf level, then you conquer. Conquer meaning here you join those left, right, and then the set where pivot elements are equal. Okay. So here is a little bit of how we partition the set. Okay. It gives you some time complexity there, right? So you are always inserting and removing at the beginning or at the end of the sequence, right? Remember, we are going from left to right. We are not picking from the middle. So in terms of accessing those things, it's order of one time. We can access it right away. But if there n elements, right? Basically the partition step of a quicksort takes order of n times, because every element is accessed in one time, but there are n elements, so it will be order of n in terms of partitioning it, like breaking it down into LEG. Okay, so shows you the algorithm here. Okay. And you can see how the same thing that I showed you earlier. You can see how the how it develops as an illustration. Right. So you have to select a pivot 6, C2431. It goes 1 1. Pretty much similar to merge sort. I just gave you the illustrations, so that way when you are practicing before you go to the exam, you can see how that develops. This is a very, very legitimate question in a final exam. Whoever the examiner is, they would give you the top note 72943761 type of a thing and ask you to illustrate, choose a pivot element. They probably would give you a pivot element like here I gave you 6, and they'll ask you to draw the tree like this. Okay, you should be comfortable doing that. So if you, after I show you this one, then you will remember it. Okay? Because the basic concept of breaking this into two trees is very simple, right? Elements less than the pivot element go into one set, elements greater than pivot element go into another set, and elements equal to pivot element, they all remain in one set. And you don't break that pivot element set. You recursively break the left set and the right set. Okay. Now, what is the problem with quicksort? In general, it works. Okay. Problem is if you don't choose the right pivot, right? Especially if you choose the minimum or the maximum element, right? One of them would have n-1 element, the other has size 0. Okay. And if you do further analysis of the algorithm that I gave you there, you will actually see that the worst case running time is order of n squared for quicksort. Okay. So, couple of other things here. I actually eliminated some slides here in the interest of time. I did not put them in the review. But then, going back to the overall complexity of quicksort, the height of the tree is log n. By now you pretty much know that, right? When you have n elements and you are doing a binary tree, basically you're breaking down into half, right? So it's log n, the depth that we talked about, depth of the tree, right? Now, that is log n, but at each level, right, the work that you have to do on the nodes itself, right, is of the order of n. So that's why you get the running time of n times log n. N comes for the work at each level because those elements still have to be put in the right place, right? And then log n comes because you are traversing the tree of depth, log n. So by now you can pretty much see how we moved away from counting instructions to arriving at these numbers almost mathematically, right, or in an abstract way. Here is a table that shows some times for you. Remember, quicksort, even though it is n log n, if you don't choose the pivot, like if you choose a wrong pivot, it could go up to n squared, order of n squared. But in general, it is n log n. Well, quicksort or merge sort. I have a very nice link for you guys. I know you are all very anxious about the exam, right? There's a student who created this big O cheat sheet where he actually talks about, I think I might have that. Let's see if I can open it. Yeah. Are you seeing my screen here? Let me share my screen for a second. I just clicked on that link. Beautiful link. I don't know if you nice guy. He says he put it together because here all the students, including my sons, right, who just got their jobs and all that, they are really grilled on these data structures. If they're a computer science student, they are grilled on big O's and things like that. Okay? So he put together a beautiful thing here. You can see here. In terms of space complexity, right, of arrays, stacks, linked lists. Remember we talked about saying, hey, the algorithm may be good if you choose the wrong data structure, then your algorithm those couple of those things like that. Here are the logs for quick sort, merge sort. What do you see here? See this one here, the best is they both are the same. Average also is the same. The worst is in the worst case, this can go to, quicksort can go to n squared. Now rule of thumb for you to remember is that the pivot element is at the extreme left or extreme right. Rule of thumb. Okay? That means one division would have 0 records and the other one would have n minus 1 records because you don't include. So that's the reason why in the worst case quick sort gives order of n squared, whereas merge sort stays consistent n log n. And if I ask you why you got n log n, because the tree depth is log n, and at each level of the tree, the processing that you are doing is of the order of n. So n times the depth of the tree, n log n. Okay, now this is here. So you can see some graphs and all. Okay, good, very excellent site. So once when you are prepared for these things, you can actually go there and take a look at that. Okay, that is that. So we'll get into Unit 3. Okay? Questions, comments? I hope the review was reasonably helpful. That's what you're doing at every level, dividing it into halves. Okay, that is the divide. Then once you reach the lowest leaf nodes, then you start conquering. To conquer means to put it back together. That's what we do in quick sort as well as merge sort. And both of them have the n log n as the best and average cases. Only in the worst case where you don't choose the pivot right, then the algorithm degrades to in quick sort to order of n squared. Okay. Tony Hoare, my favorite person who invented quick sort. Interesting tidbit. The professors there, Tharmagaru and others would appreciate. Recently, actually, I saw his picture with a colleague of mine from Middlesex University, somebody who I know. I actually never knew that Tony Hoare did not have a PhD. I wouldn't say just, he's a lecturer. I don't know if he's a professor or not. I think he does not have a PhD or anything. But great man. Okay. Now let's talk about greedy methods. Okay. Remember Gopal? Some of those things we discussed. I was putting together some of these things and not necessarily in that particular order, but we'll see. I think I'll discuss span trees first on Gopal. We'll figure that out. I do not have a review of job sequencing. I didn't get to put that, but we have done a couple of job sequencing problems. If possible, by next class I'll try to put it as part of the slide deck. Okay? Okay. Let's jump into it. So what exactly is a greedy method? Right? I think in India, most of the tests, they are very big on definitions and all that. At least when I was growing up, that's how it was. I used to have so much difficulty memorizing some of this stuff, believe me. I can solve problems, but I cannot memorize stuff. But in India, we need that also, that skill. So, the scenario is this. We have to make decisions with imperfect information. Imperfect in the sense you don't have all the information with you handy at one place to make the decision. Okay? So you have intermittent data that you have to make the decisions. So that is where you use basically the greedy method. And in the process what you are doing is you are trying to optimize it locally. Locally meaning in your immediate vicinity. And the hope is all these local optimal solutions will finally add up to a global optimal solution. Okay? That is the hope. It's actually kind of like this. If you look at the global warming problem, this actually might work. If everyone locally really worries about the global warming, globally it could actually achieve that. We always say, hey, yes, a lot of optimization problems are there. Some of them can be solved using the greedy method. But others are there which we cannot solve using the greedy method. The classic example that we give is knapsack, right? Knapsack you cannot solve with the greedy method. And whenever I talk about knapsack, you should always go back to from an exam perspective, go back to the counting of coins example also. You cannot solve the counting of coins problem optimally using the greedy method. Okay? It works sometimes, and most of the time it doesn't work in terms of optimization. You're optimizing scheduling, you're optimizing shortest paths, there are different optimization criteria. Okay? Now let's look at behavior. So here is a trivial example, right? So you want to pick k numbers out of n numbers. because, and the k number that you want to pick, you want to get the sum of those numbers to be the largest. So for 1 to k, for I equal to 1 to k, pick out the largest number and remove it from the input. Then you go again, pick the next largest number. Fairly trivial. So do the thing as finding the shortest path. Okay. So you are going from V0 to V3 here. You have different decisions to make. Remember, it's all about decisions. Okay. Now when you're starting from V0, the only data that you have is, hey, how can I get from V0 to V1? Right? You don't have rest of the data. Now, in this case, it turns out it's almost like a single source. So you are able to come up with the shortest path here. And you will get to that. However, consider this one here. Okay. Now, all of a sudden, what happened is you have multiple nodes in intermediate stages. Okay. It's not just one node like in the previous like you have multiple nodes. Now, if you are applying the greedy method, what does the greedy method say? Okay, I'm optimizing what here the path. So you go from V0 to V12. The reason why you go to V12 is it compares 3, 1, 5 and 7. Right? But you can see here, when you have a multi-stage graph here like this, not give you an optimal solution. Okay? Very important to, I would say this is one of those graphs that you should memorize at a high level. Multi-stage, the concept, you are memorizing the concept, a multi-stage. It's a legitimate exam question saying, hey, give me a counter example to the shortest path where the greedy method does not work. Right? The questions are never phrased in a straightforward way. So if you can kind of carry this image in your mind, then it's easy for you to show that continuity example. Okay? So in multi-stage it doesn't work, in knapsack it doesn't work. Now when you're doing the greedy algorithms, one of the predominant things that is used in arriving at the solution is the concept of spanning trees. The goal here when you're applying this algorithm is to always figure out the minimum spanning tree. Now we discussed a whole bunch of the concepts associated with trees, and I put a Word document for your internal exam. You will see a whole bunch of definitions related to this. Okay. So what are some of the definitions here? You need to know what a tree is, you need to know what a spanning tree is, and you need to know what a minimum spanning tree is. Okay. Tree is nothing but a connected undirected graph with no cycles. Remember, it cannot have cycles. It should always have a root, and then it should grow from there. Okay, it's undirected. It's not a DAG. DAG is a directed graph, right? Now, what is a spanning tree? We are always talking about spanning tree of a graph G. If it spans G, what it means is every vertex of G is included. It's a subgraph of G, meaning every edge in the tree belongs to G. You cannot come up with an edge in a spanning tree where that edge is not there in the original graph. That cannot happen. Okay? So now once you know spanning tree, then minimum spanning tree is a logical extension, right? Because if the edges have weights, if you come up with a tree, a a spanning tree with the smallest total weight, then it becomes the minimum spanning tree. Now that is all easier said than done, right? The question then is, how do you right? That is a trick question, right? How do we compute them? Let's see if I have some examples here. So here is a remember I told you I'll make you do some quick exercise in the class today. Here we go. So I give you a tree there. A B C D E. That's a tree, right? Now it's not drawn in the shape of a tree. Basically it's a graph. I shouldn't say tree. It's a graph. It's not a tree, right? It's a graph. So take 5 minutes. 5 or actually even 3 minutes, okay? 3 minutes. Draw a spanning tree for that graph that I showed you. Remember, you cannot draw a minimum spanning tree there. It is, I did not give any weights. It's just a spanning tree. Whoever gets the answer first can put it in the chat. Just take 3 minutes. I do see Jntuk picture, so I see them doing it. I'm assuming they're discussing that. They're taking a sheet of paper. That's good. I'm assuming you're still able to hear me. A-E-B-E-C-D. A-E. Okay, and then C-B. How can you get a cycle? You have A-E-B-E. You cannot have a cycle in a tree. Your work? There is no cycle. How are you drawing that? So let me see. Let's use the whiteboard. A E B C D. There you go. See, because there in the first thing there you put. Yeah, there it is. Yeah, you got it. Okay, that's one. Anyone else got another spanning tree? In the exam. I know I have not seen your final exams, any copies, but I'm positive that they'll give you some examples like this, make you draw spanning trees and minimum spanning trees. Okay, let me see what I have here. Couple of them. Okay. So there can be many spanning trees. It's not like you'll have one unique spanning tree. Okay, A, B, E, C, D. I think you are referring to this one, I think. S, V, C, W, the one on the right. A, B, E. Like that. Okay. Somebody could have gotten AE like this, the one on the left. It doesn't matter, right? There are many spanning trees. And there are lots of, if you are a mathematician, they will figure out, right? They beat it to death. How many you can have, how many spanning trees you can have, and all that stuff. Okay. Okay, good. Now let me see what I have next. So this shows you how do you programmatically, right? So there are two ways of doing it. Remember, it has a graph as what? Vertices and edges, right? So you can start with an edge or you can start with a vertex. Actually, that's what Prim and Kruskal have done, right? Kruskal started with an edge and Prim started with a vertex. Remember in the beginning, when we were waiting for the rest of the colleges to join, we discussed that. I was talking about that with Gopalakrishna of Jntuk Moocs. Okay. So how do you do it with vertex centric? I don't think they would ask you pretty easy. Okay. So you are picking an arbitrary node and calling it as being in the tree. Now a spanning tree, remember what is the definition of a spanning tree? It should include all the vertices. It never said it should include all edges. It only said it should include all vertices. Spanning tree means all vertices. Okay? So then, after you select one arbitrary node, then you pick some other arbitrary node in the tree with an edge E to node W0 in the tree. Okay? And then you keep adding it. So you keep repeating that until all the nodes are marked. So if there are 5 nodes, you do it like what? 4 times. The loop is 4 times basically. Okay, n minus 1 times. Okay? Because there are n minus 1 vertices that have to be added to the tree. Because you have already added the first part, right? So you go through that loop, repeat until that's 4 times, if it's 5 nodes, and then you come up with a spanning tree. Now in the case of edge centric, now that second step is where it differs from the vertex centric. So as long as we have more than one tree, connect 2 trees together with an edge in the graph. So that means now you are hunting for an edge in the graph. Okay? As long as that edge is there in the graph, you can connect those respective nodes, right? Remember, a single node also is a tree by definition, right? Okay? Again, the second algorithm also does n minus 1, order of n minus 1. Okay? Now, efficiency, of course, is dictated by how quickly we can tell if the edge would connect 2 trees or would connect 2 nodes already in the same tree. Okay? So that is like doing the spanning tree. Okay? So here is a tree where we are using the edge-centric example. So we are taking the edges of the tree in an order, put them in a list. So in this case we have A, B, BC, CD. Where is CD? Yeah, CD, and then AE, BE, and CE. Right? So if edge-centric, what I do picture after that, each of these things is a tree by itself. Nothing is connected. All the nodes, okay? Now you have to select one edge from the list. And then we are going in order. So you are going to do AB. Now when you take AB, the AB is in the graph, right? That's how you came up with the list order. So you connect A and B. Then you have BC. Right? So you go here, you see, you connect BC. Then after you connect BC, then what do you have? CD, right? So CD exists, so you can connect CD. So I'm here now, second row, first one. Okay. Once you connect CD, Now once you connect AE, then you have BE. What happens when you have BE? What would you do? I only stopped after AE, right? Why I did not do BE? Can anyone answer that? There is cycle, correct? That is a good, excellent point. There is cycle. But what about one more observation? Besides that, there is one more fundamental observation, right? Anyone wants to take a shot at it? We got all the trees connected, right? Cycles are not considered, you're absolutely right. But we also got all the individual trees connected, right? To begin with, we had A, B, C, D, E as trees, correct? Single node trees. And you stopped once they are all connected. Now, that is the reason why you don't do BE and then CE. You stop once you stop there, there would not be any cycles. Because you have to maintain the tree structure, right, by default when you're constructing this. Okay, good. I hope you like this example. Good. These are the type of questions that you will definitely get in the exam. Okay. The next slide basically shows a minimum weight spanning tree. Okay, minimum weight meaning, remember we talked about spanning tree. Now we want to figure out minimum weight. Same node structure. Okay. Except we are now taking the additional construction. Okay. Now, you don't need to memorize this one, but try to understand it, right? There is this property called a cycle property. When you have a some node C, which belongs to E, be a cycle, right? And then you have that E as an edge of maximal weight in C. Okay, so that means when you see a cycle and one of the edges there in that cycle has a maximum weight, then it does not need to be in a minimum spanning tree, right? Looks pretty obvious, right? Intuitively, when you have a cycle of edges, you want to take the least weighted edges to come up with a minimum spanning tree. Okay, that is called the cycle property here. Okay, so 9 for a given graph, minimum spanning 9 for the given graph. Okay, could be. We'll find out. I don't remember. You could be right. Yeah, I think so. Great. Now let me go to the next slide here. Yeah, we got 9, correct. Was the answer given by a student or the faculty member? The reason I introduced that cycle property there in the review is that is what Kruskal algorithm uses actually. Okay, he does not take the maximal weight when there is a cycle. He does not put that edge of maximal weight in C. Okay, it won't be in the MST. SVCW gave the answer correct. Is it a SVCW student or was it SVCW faculty? what I asked. I'm sure it will be student and then faculty type for them. Okay, great. So that cycle property again is nothing but in a cycle students. Perfect. I'm so happy. That means students are learning something. Okay, good. So how does it work? So you are basically sorting all the edges and increasing weight of product, number one. Remember, even earlier when we had those edges, we sorted them, we put them in some kind of an order, right? Here, in order, okay? If the edge does not create a cycle, add it to the spanning tree. Otherwise, discard it. Okay? Now, when do you stop it? When you have n minus 1 edges. The reason, and why is it n minus 1? Remember, we had this property between a tree and the number of edges a tree can have. It's always one less, remember? When you have a tree of n nodes, the number of edges is n minus 1. Okay? So, those are the two steps to create the minimum spanning tree. Now there's some this E times log E. E is the number of edges. Okay. Now the second thing is, as it says here, right? How efficiently you can check if adding an edge will create a cycle or not. Okay. Again, going back, the mantra sees n log n seems to be coming everywhere. Remember that? Wherever there is a tree, I mean, it's a pretty easy thing to remember, right? In the exam, you should not get confused. The reason why n log n is, hey, it's a tree. Tree means log n automatically comes, okay? Unless you're doing some super special you have at every level you have some work to do, right? There are n elements, remember? There are always n elements. The reason why we generalize it to n is if n tends to infinity, at every level you in essence have infinity element, right? Infinity broken down binary to two things, it's still infinity. You don't say infinity by 2. That's the reason why you take n. So you go log n depth. At each level you do n times n. So if it's by n times log n. So it just shows that algorithm. We did, right? So how are we doing it here? I'm giving you a solution there. I took the edges, they are sorted, right? Now when you have the same value, you have a tie break, right? You can choose anything at random, whatever your algorithm is, right? So I use those things, take each edge, start putting it together. That's what this says, right? So after you do A, B, and C, E, this is what you get here. Steps, and you will convince yourself that this is the answer. Okay. Again, a simple, easy to understand example, which will give you 100% concepts to be ready for the exam. Here is another example that I had. Did not really pay attention to this one, but you have a graph on the left and you can see the minimum spanning tree there, how the author came up with the minimum spanning tree. You can convince yourself that that is indeed a minimum spanning tree, okay, applying those two steps. What does Kruskal's algorithm do? So it is sorting all the edges. Remember, Kruskal is edge driven. Prim is vertex driven. I asked the question in the beginning when we were waiting for the students. So you are sorting all the edges. That's exactly what we did in the previous couple of slides too, right? In a non-decreasing order, meaning it's ascending, right? Okay. Then you are adding the next smallest weight edge to the forest. And why do you call it a forest as opposed to a tree? In prim, when I talk about differences between this one and prim, in prim, but you are building the tree from one root node. Whereas in cruscal, they are n vertices, you have a forest of n trees, because each node by itself is a tree. Okay? So till all the nodes are connected, you call it a forest. Because a forest is made up of more than one tree, right? That's what a forest is. Okay? That's why in cruscal we call it a forest. And then you stop once you reach n minus 1 edges, because a tree of n nodes will only have n minus 1 edges. Okay. I think this much you can memorize. I think it's a pretty easy thing to memorize these 3 steps. Actually, if you practice a few times, you don't even need to memorize. You understand it intuitively also. Okay, now let's see. So here is a spanning tree. So you have a graph here. Remember, you need to have a graph. And then you graph as how many? 1, 2, 3, 4, 5, 6. So what is the first step? Each one, you put it here. 1, 2, 3, 4, 5, 6. Okay. Now you have a sorted order of edge list. Remember, non-decreasing order, meaning it's an ascending order. I don't know why they have to call non-decreasing. Why can't they call it ascending? Okay. So you have edge 1 to 2. You know the value can go. Okay. Next is edge 3 to 6. Where is 3 to 6? 3 to 6, 15. Okay. So you put all the edges in ascending order like this. Okay. Now you pluck the first element from the list. First element is what? 1, 2, right? Because that is the lowest. You take that one, connect. Okay. So then that is connected. Then you take the next element. You can see that step there, right? No cycle is formed. Remember, we are always checking that no cycle is formed. Okay. Next is 4, 6. So can you connect 4, 6, 20? Yeah, you can connect 4, 6 like this. Okay. And next you connect 2, 6. Okay, 2, 6 is connected here. Okay. So still no cycle. Now at this point, if you see, the only node that's remaining which is not connected is 5. Okay. Now, but look at what happens when you have 1, 4. When you connect 1, 4, is there a cycle? There is, right? 1, 4, 6, 2, 1. Okay. You connect 3, 5. Okay. Now how many edges you got now? 1, 2, 3, 4. 5. You got 5 edges now, right? 5 is 1 less than the number of nodes. So you stop. Got it? Very cool, huh? Once you have these algorithms and tables and all that, it's easy for you to trace that. Okay, now cruscal versus prim. I don't have prim example here. You can easily Google up a prim algorithm example, or you can go back and review our slides. So what is the difference between cruscal and prim? prim you always keep a connected, meaning you start with one vertex and then you keep connecting from there on. Okay, you're still looking at edges, okay, and you're finding the smallest among them. Okay, so that is the modus operandi there. Start with a vertex, find an edge, okay, from the current component to the other vertices, and find the smallest one among them. Keep adding the smallest one. Okay. Maximum steps would be n-1 steps, right? Because okay. And crucicles, you do not keep any connected component. Because everything you start with a forest. Okay. And again at each, I did something there. Okay. At each stage you are looking at the smallest edge that does not create a cycle in the current forest. Okay. So when you are connecting it, you are basically merging two trees. Remember, everything is separate tree, right? If they are n elements, they are all n trees. So as you keep connecting, merging the trees in essence. Okay. One graph. Okay. Now, crucicle versus prim. Same thing, some additional notes on that. Okay, I wrote them in different ways. Okay, both are greedy algorithms. Okay, so in prim the graph has to be connected, but that's not true in crucicle algorithm, right? One of the primary things you should note here is then which one. Dense graphs. What is a dense graph? Meaning you have a lot of edges. If you have, let's say, a fully connected network, it's a very dense graph, right? So in those cases, prim's algorithm runs faster, whereas crucicle runs faster if it's a sparse graph, meaning the number of edges is less. Okay? So rule of thumb, if the question comes, say which one will you use, you say a graph with lots of edges, you would use prim's algorithm. Okay, questions, comments? I just have just a couple of more slides and then we can wrap up. I know it's 12. Knapsack, right? So you all know what knapsack is. You have this thief guy enters it. You have different items with different weights and values, right? And then knapsack has a limit. So how do you maximize the profit is what we're talking about here, right? So one way of looking at it is it does not have a greedy algorithm, does not work for knapsack. Because greedy, if you go by the greedy algorithm, right? It always tries to take the one with the highest weight, right? Okay, highest weight is 3 pounds. So it will get the value how much? 100. Correct? But if you do not do the highest weight, if you do it in a different way, the value is 300. Sorry, I'm not saying just take that. 300 is what you get. Because you take 3 pounds, because that's the greedy algorithm. You want to fill up the bag as soon as possible, right? You take 3 pounds, you get 300. But that is, and you can't take any more because you exceed the weight limit. So you are happy with $300 or 300 rupees. Okay. Whereas case of solving it, including dynamic programming, as we talked about in one of the classes, right? You would choose this 2 pound and 2 pound, right? When you choose these two, you can see you have maximized your weight, perfect weight, and then you have maximized your value to 190 plus 180 gives you 370 as opposed to 300. Okay. Just wanted to do that one because we discussed knapsack quite a lot, but I give you an illustration here again. Okay. Now, what is the single source shortest path problem? That was the other thing that we discussed in this chapter. All we are doing here is of shortest path problems. Okay. In the case of single source shortest path, what we are saying by definition is the shortest path from the source to all other vertices in the graph. Remember, anything to do with traversal, you model it in the graph, right? Like remember we talked about the traveling salesman problem. In the very first class I said go look up the Dijkstra's algorithm that uses this single source shortest path. All you're doing is finding the shortest paths from the source vertex to all other vertices. Which one you are referring to? I didn't see it. Sorry. I did not see that. Okay, could be. Whatever you said, I say it's correct, right? But I did not see it. You also said no, meaning for some other MST maybe. Okay. So whenever you talk about shortest path problems, you have some kind of a directed weighted graph. Okay? And the path is nothing but the sum of the weights. Okay? And the vertex at which the path begins is called the source. Okay? And of course where it ends is the destination. There are some ways of doing it. I'm not really focused too much on going into too much detail here because we covered this significant. So you have a source node 1 and destination node 7. Then how much it costs, that's what we are trying to find out, right? That is one way of looking at shortest path. So if you see the direct path between node 1 and 7, node 7 here, is here, right? It's going to cost 14. Okay, you have a shorter path which costs only 11. So how do you determine these things? This is where you use that monthly shortest path algorithm and so on, including the famous Dijkstra's algorithm is based on that, right? Okay. And then you solve the problem. I actually made you look up Dijkstra's algorithm if you recall, right? In the case of traveling salesman problem. Now, these are all the different, we didn't really cover this in our class, but I thought let me put it here. There are different variations of shortest path, right? You have single source, single destination. And then you have single source, all destination. That is what this. Each and every vertex. By doing that, you're actually, that is what Dijkstra's algorithm does. Okay? That's how you solve it, optimizing your travel route. You also have single destination shortest path, which is like once you have two variables, you have four combinations, right? 2 raised to 2. We know that. So you have source and destination. So combinations of those two would result in these 4 different ways of doing it. We also talked about all pairs shortest path, if you recall. When we were talking about dynamic programming, I think we talked about that. We'll visit that also in some about these shortest paths. I'm done. Just is the subpaths of shortest paths are also shortest path which would violate this condition. I showed you a cycle there in one of the pictures I remembered, and then we did a basic true and mathematics. Okay, and shortest paths have no cycle. The definition of path will not have cycle. Okay, and then we talked about this property called triangular inequality. Remember, when you have ABC. Talked about in an appropriate way. I wanted to end saying that, hey, what is the example of these things? Dijkstra's algorithm. So your task, even if I have that slide open for Dijkstra's slide closed, your task is once again going back to square one. We started off saying, hey, go visit Dijkstra's algorithm, right? I gave you some notes here, right? If you go back and you can see the graph here, right? Take this example. Okay, you already know what the shortest path is, right? Take this example, run. Same thing, you trace Dijkstra's algorithm on this example, and then convince yourself that that algorithm works and it gives you cost level. Everyone understand the problem? Okay, I assume silence means you all understand or you don't care. But since you're all great students, I assume you all understand.
Actually, I thought,
Okay, so that completes up to unit 3.
I would have done it.
Next class we will cover unit 4 and 5 and if time permits unit 6. Unit 6 should still be